So in this section, we're going to be looking at series, and a series is simply adding the terms in a sequence, which we talked about last section. So an infinite series would be continually adding all the numbers in a sequence forever. And surprisingly, sometimes an infinite series can have a finite sum. If we look at this example here, if we add 1/2, 1/4, 1/8, 1/16, and we look at something called partial sums. So partial sums would be when you add just a finite number of terms in a series. So here we would have 1/2 from just the first term. When we add the first two terms, we get 3/4. Add the first three terms, we get 7/8. Add the first, four terms, we get 15 sixteenths, and so on. And you'll notice that each of those sums is getting closer and closer to 1. So we're making the conjecture that this series, if it goes on forever, that sum will eventually approach 1. And so to look at that, we're going to look at those partial sums again. So let's look at some of the terminology. We have this sigma notation, which you know means adding those. So this terminology means adding the terms in the sequence S of n. And so when we do that infinitely, we have a series. And then when we do that to a certain amount, we have a partial sum. So here, if we're going to find the sequence of partial sums of this particular series, the one we just talked about, you'll notice that each of the terms in that sequence were 1/2 to the n power. And in fact, when we want to determine what S sub n is, we can look at each of these partial sums. So S sub 1 is 1/2, which is the same thing as 1 minus 1/2, and you'll see why I'm going to do that in just a minute. S sub 2, we said, was 3/4, and that is going to be 1 minus 1/2 squared. S sub 3 was 7/8, and that's going to be 1 minus 1/2 to the third. So we can see a pattern here where S sub n is going to be 1 minus 1/2 to the n. That's what we're getting each time. So then when we look at the limit as n approaches infinity of 1 minus 1/2 to the n, we know that this part right here goes to 0. This part right here is 1, so that limit is going to be 1. And so then we know that our sequence of partial sums, that this series is going to converge to 1. So we say that this is the sum of the series, that's the limit, that if we kept adding the numbers in the series forever, we would eventually get to 1. So our series converges and the sum is equal to 1. Those are the terms that you would use. If the S sub n goes to infinity, then we say that that series diverges. And again, if the S sub n does not exist, we also say that that infinite series diverges. So the series only converges if you can come up with a number for the sum. So in this example, if I want to find the sum of this series, you'll notice that this, when we plug in the different numbers for k, we get 1/1 times 2 plus 1/2 times 3 plus 1/3 times 4, and so on. So S sub n is going to be equal to 1 over, and we always have n, and then n plus 1 each time. Well, if I do partial fractions with these right here, I end up with 1 over 1 minus 1 over 2. Then this one gives me 1 over 2 minus 1 over 3. The next one gives me 1 over 3 minus 1 over 4. And that keeps going until I get to 1 over n minus 1 minus 1 over n, and then 1 over n minus 1, or plus 1 over n minus 1 over n minus 1. So here everything cancels out until we're left with only 1. So then we can say that that sum of that series is equal to 1. So you'll notice for each of these that we had to come up with a pattern, and we had to come up with a formula for finding that sum of that series, for finding S sub n, in order to be able to tell what the sum was. If we just want to know whether a series converges or diverges, then we need to figure out if it has a sum or if it goes to infinity. So this one, if we're just adding numbers, well, we know that we just keep going to getting bigger and bigger and bigger. And when we add all those together, we have this formula where you add up all the counting numbers, divide by 2. That's how you can get the sum of all the counting numbers, is by doing n times n plus 1 divided by 2. And we know that limit goes to infinity because this number up here just keeps getting bigger over 2. And so since that's going to infinity, that series is going to diverge. We have what's called a geometric series. So a geometric series is one where you have some number times a number r, ratio r, and that's going to be to the k minus 1 power. So that gives us a first term, and then we keep multiplying that first term by multiples of r. So we use r to decide if that series is going to converge or diverge. If we have a geometric series and the absolute value of r is less than 1, then that series is going to converge. And if the absolute value is greater than or equal to 1, then that series is going to diverge. So here you can see all you're using is r in each of these to determine whether it converges or diverges. Make sure you're using the absolute value of r, okay, and these absolute value of r is less than 1, so both of those are going to converge. Here it's greater than 1, so it diverges. If it's not in the form, in this form, you have to make it be into that form. And so here we can change this to this, so 1/2 times 1/2 to the k minus 1. And then we have an r of 1/2, and so we know that that series converges. And then here, also not in the form, so it needs to be put in the form. And once you get it into that form, 1/3 is less than 1, so that converges. and then this one diverges. And each time when you figure out what it converges to, you're always doing 1 over 1 minus r, and that's going to give you the sum of your series, what it converges to. So you can use this to figure out what fraction a repeating decimal is, because repeating decimals can be written as geometric series. So if we're going to write this, that's going to be 0.09 plus 0.009 plus 0.9. And if I write those as fractions, I have 9 over 100, 9 hundredths, 9 ten-thousandths, and then 9 millionths, and so on. So we can write this as a geometric series by saying we start with 9 over 100, that's the first term, and then each term we're multiplying by 1 over 100 to some power, the k minus 1 power. Once we have that, then we take that first term and put it over 1 minus r. And so that's 99 over 100 here. So we get 9 over 99, which is 1 over 11. So 1 over 11 is going to be our repeating decimal, the fraction that gives us that repeating decimal. A harmonic series is a specific kind of infinite series. It's the one specifically that is the sum of 1 over k. So 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 and so on. A harmonic series diverges. You're going to want to recognize that harmonic series. It's going to be really important later when we look at different kinds of series to determine if they converge or diverge. We can compare them to a harmonic series, and so it's important to know that a harmonic series diverges. Recognize what it is and that it diverges.